Okay, so we're starting to shift our analysis to looking at categorical data. And we did a little bit of that with the z-tests for proportions, a difference of two proportion z-test. Those percentages represented categories of this percentage of the sample that we surveyed believes this or has this opinion, and we compared that to somebody else. That was good, but it had some limitations, and we're going to talk about those limitations today and kind of previewing the need for a test that looks at things more in the big picture, and that's what this test does. This is called chi-square. This X-looking thing is the Greek letter chi. Okay, it looks like chi, but it's not. It's pronounced chi. And the squaring part of it you'll see as part of the equation in the calculation by hand. Like we've seen before, the squaring is to make everything positive. Okay, we'll be looking at differences. Some are positive, some are negative. We want everything positive for our analysis. That's where the square comes into play. So our big target for today, use this chi-square test to identify relationships between categorical variables. Now, yesterday we spoke about these two-way tables, and the Z procedures that we spoke about in chapter 18 allowed us to compare proportions of successes between two groups, either two populations or two treatment groups in an experiment. The limitation, though, is when there are more than two outcomes, or when we want to compare more than two groups to each other, we need a new statistical test. Okay? Otherwise, we have different p-values. Like, we were comparing like the male opinions to the female opinions in a lot of these groups. Or we had like a younger category and an older category that we were comparing against each other. But what if those classifications are too broad? Like, what if you wanted, like, how do 20-year-olds feel about this? 30-year-olds, 40-year-olds, 50-year-olds, 60-year-olds? Because maybe illustrating that change over time can be very important. Well, if you're to do that as a z-test, then you have, like, 20-year-olds compared to 30-year-olds, and 20-year-olds compared to 40-year-olds, and 20-year-olds compared to 50-year-olds, and 30 compared to 40, and 30 compared to 50, and 30 compared to 60. You could end up with like dozens of different p-values, some of them significant, some of them insignificant. And how do you sort through all of that and try to make some conclusions based off of, like, well, is there a legitimate change over time in your opinions or the way people feel about this thing? Do they differ based off of that age breakdown? The Z procedures for a difference of two proportions is just that. It allows us to compare two things. But if we're looking for a broader comparison, we need to use something else. And that's where this chi-square test and the summarization of data on this two-way table can be helpful. So the key word for this lesson is relationship. And this new test addresses a general question. Is there a relationship between two categorical variables? So that's a very vague term, but that's kind of a good thing. Because what you're going to see here is that unlike what we did with the z-test and the t-test, okay, we ended with a p-value, we reject the null, or we fail to reject the null. Okay. Yes, I did want you to interpret your conclusions, like what does that mean in the context of the problem? But we were essentially done at that point. With the test we're looking at today, we get our p-value, we reject the null, or fail to reject the null, but then if there is a relationship, if that's what our conclusion tells us, our work is just beginning. if there's a relationship, now we've got to dig into this and see exactly what that relationship is. Okay? So the test itself, I don't know, it's not that bad, it's not that difficult. It's just different from what we've done. In all honesty, if we were to look at this test first without any background knowledge of the z-test or a t-test, okay, you might just think, okay, this is the way it's done. And you just do it. Okay? But there are differences between what we've done before and what this is looking at now. And again, at the end of that test, now we need to kind of look at what these results mean. And that can be a little bit complex. We're going to use this example problem for like all of our procedures today. It's a sample survey that asked a random sample of young adults, where do you live now? And we have this table that summarizes the results from our sample of almost 3,000 people, 2,984. Both men and women are grouped in here, and they were classified by their age and by where they live. Okay. Now, living arrangement is one of our categorical variables, and that's broken down. These people can live at their parents' home, they can live in another person's home, they can live in their own place, they can live with like several roommates, or they could live in some other arrangement. Now, the other variable about age says even though age is quantitative, the two-way table treats age as dividing young adults into 4 categories. Kind of like what I spoke about yesterday with grade level, 9th, 10th, 11th, 12th grade. Yes, those are numbers, but that breakdown into 4 different categories allows us to treat it as categorical data. Same thing here. We are just concentrating on these 4 years, ages 19 through 22, so they are going to serve the purpose of categories here. Now, when we're looking at this table, remember I said yesterday, for our dimensions, we do not include any totals. So we have 5 breakdowns in the living arrangement, and we have 4 breakdowns for the age. This is a 5x4 two-way table that we are looking at. The other thing, when you're asked to identify what variables are being compared, the 2 variables are living arrangement and age. Sometimes people want to look into it too much and say, well, a variable is living with the parents, or living with somebody else, or living in your own place. No, that is the breakdown of how the variables are measured. But the 2 variables that are being compared, okay, essentially what we want in our hypotheses are living arrangement and age. Now I have a few questions down here that are answered over the next couple slides. First one says, calculate the conditional distribution in proportions of the living arrangement for each age. You're going to see this phrase, conditional distribution. Okay? It's a percent. Okay? We talked about that marginal or conditional breakdown of the two-way tables. A conditional distribution is just the percent. So for example, we could look at a column or a row percentage in this case. If we were to look at the column here, these 324 19-year-olds who live with their parents. 324 out of 540 19-year-olds surveyed, that's about like a little more than 50%. Yeah, that's exactly 60%. So, we have 60% of the 19-year-olds live with their parents. We could calculate a percentage for living in somebody else's home or their own place, all the way down in that column. We could do the same thing for the 20-year-olds, the 21-year-olds, the 22-year-olds. If we wanted to, if it was relevant for us, we could also work across horizontally. Those 324 19-year-olds who lived in their parents' home, what percentage of all of the people who live in their parents' home were 19-year-olds? 324 divided by the 1357, that's like 23.9%. That is a little bit less relevant in this case, okay? Because you're just looking at all of the people who live in their parents' home and how they fall into those four categories. That statistic is a little less relevant than the percentage of the 19-year-olds, okay? Because this could kind of be extrapolated to the larger population, hopefully. But sometimes you'll see that with your analysis. Sometimes the vertical proportions make sense or are more valuable. Sometimes the horizontal ones are more valuable. Okay. We're also going to be looking at a graph to kind of visualize these differences. And we also want to determine, are the distributions of living arrangements under the four ages, are they similar or are they different? Okay. And we want evidence from both these percentages and from the graph to help support that. Well, I looked at one of the percentages in the top left there. We have a lot of other percentages to look at. Okay, I just did it for the 19-year-olds that lived in their parents' home. Okay? But that was one of 20 possible ratios that could be made in that vertical column. Again, I said in this case, the rows, those percentages don't really make much sense, and those aren't even considered right here. But it's very easy to kind of look at this and just like glaze over and say, blah, like, how do you expect yourself to make sense of all of this? Well, sometimes a graph can help. Okay? If we were to plot this just by looking at these percentages of each age group who live in these different breakdowns, we can see that that percentage of 60% of the 19-year-olds who live with their parents, that was the highest of any breakdown here. And in fact, we can look at change over time, this first column in each of these age groups, 19, 20, 21, 22. There, to there, to there, to there. The proportion of people who live with their parents goes down as their age increases, which is kind of to be expected. Okay? We see that illustrated on the graph, which wasn't necessarily evident just by looking at the numbers. Okay? Either the numbers on the table, okay, or the numbers in the percentages right here. Additionally, we can kind of see that, well, the people who own their own place, the third column, starts pretty low, and it continues to go up and up, almost to the same level of the percentage of the 19-year-olds living with their parents, almost to 60% by the age of 22. So we can see these changes across the categories. But what we can't see is, does there appear to be a relationship between your age and your living arrangement? Some are changing. Yes, we see that. Is that change significant enough? And again, if we were to do a bunch of difference of two proportion z-tests, again, we're going to be doing z-test after z-test, p-value after p-value. Some are significant, some are insignificant. What's to tell you what's valuable and what's not? Okay, we need to take a step back, look at the big picture. Is there a relationship between age and living arrangement? And if that relationship comes back as significant, there is a relationship, now we can start to dive back into this and see, okay, well, specifically, which ones are of interest to us? And we can look at that a little bit closer, maybe do a z-test at that point, if it's relevant. I've already mentioned some of these. The problem with multiple comparisons. In general, it says to address the general question of whether there is a relationship between two categorical variables, we look for significant differences among the conditional distributions. Again, when you see conditional distributions, you think percents. Okay? Is there a significant difference between those percents? Now, the null hypothesis is always going to be no relationship between these two. Alternative hypothesis is always going to say there is a relationship. Now, previously, null hypothesis was always an equal sign, okay? Mu equals this, or P equals this, or mu1 equals mu2. Now we are abandoning the equation structure, and instead it's going to be a sentence, but the sentence is the same thing every single time. Okay? As a general null hypothesis, there is no relationship between the explanatory and the response variable. The alternative hypothesis, there is a relationship between the explanatory and the response variable. Now, I do want you to adapt that and insert what the explanatory and response variables are. Okay? But they say here, there is no difference in the distribution of a categorical variable for several populations or treatments. There is a difference in the distribution of a categorical variable for several populations or treatments. Don't worry about that. Use relationship. There's no relationship as the null. There is a relationship between living arrangement and age in this case. We said we could compare many pairs of proportions, ending up with many tests and many p-values. Bad idea. When we do many individual tests or confidence intervals, the individual p-values and confidence levels don't tell us how confident we are or how confident we can be in all of the inferences taken together. These do play off of each other. We are essentially testing for independence here. And we need to be aware of that relationship between the breakdown of these variables. And they don't isolate themselves. They don't exist in a vacuum. Instead, we're looking at multiple analyses going on at once here. So in the big picture, is there a relationship between these two things? Additionally, it says the problem of how to do many comparisons at once with an overall measure of confidence in all our conclusions, this is common in statistics. We don't live in a world where it's easily broken down into black and white. Okay? How does this one thing compare to this one thing? No, it's complex, and it has different ways that things could be interpreted or broken down. So this is a problem of multiple comparisons. And statistical methods for dealing with multiple comparisons usually have two parts. This first part is an overall test to see if there is good evidence of any differences among the parameters that we want to compare. That's what this chi-square test does. But let's say we go through, we get a p-value that's less than 0.05. We reject the null, accept the alternative. There is a relationship. Now our work is just beginning. We have a detailed follow-up analysis to decide which of the parameters differ and to estimate how large those differences are. So we'll get into a little bit of this at the tail end of our lesson today. But it's a two-part thing. The overall test, though more complex than the tests we saw earlier, the z-test and the t-test, it's reasonably straightforward. The follow-up analysis can be quite elaborate depending on how many different things you need to consider. All right, expected counts. In all of the tests that we've done up to this point, the null hypothesis has represented the expectation. Okay? It's the population value, or there's no difference between the two things that we are comparing. So as part of this process, okay, I've said this before, we expect this. We took our sample and we got this. So there's a difference between what we expected and what we got. The purpose of this test is to determine if that difference can be attributed just to natural variation. Okay? We expect this, we got this, it happens sometimes. Or is that difference, a difference of that magnitude so rare that the really only conclusion that we have is to say that that null hypothesis, that expectation, was wrong to start with. And that the evidence that we have from our sample is more illustrative of what is truly going on in the population. That basic concept, or that basic interpretation, does not change with chi-square. We have an expectation that's set forth in the null hypothesis that there is no relationship between the two categorical variables that label the rows and the columns of a two-way table. The alternative hypothesis, okay, we are testing to see that there is a relationship. But unlike the Z and T test, where if it's a one sample, we had a null value to compare it to, now we need to calculate what those expected null values are. So to do that, we're going to go back to something that's based off of what we saw in our probability unit, expected value. We saw different cases like binomial and geometric, but in general, if we have independent items, we can do n times p, the number of items times that probability. So as a version of this, we have two variables that we are considering and essentially testing their independence. Okay? This chi-square test that we're doing right now is called a chi-square test of independence. So if they are independent, we should be able to multiply them like this and get that expectation. So going back to our table, to get an expected count from what we observed, we are going to take the rows total for each of the cells. We're going to take the rows total, multiply it by the columns total, and divide it by the overall total for that table. In this 5x4 breakdown that we had, we are going to be doing this 20 times. Now, we're not going to be doing that because we want to let the technology do it for us. But if we were to do it by hand, we would be doing this 20 times. Let's take a look at what that looks like here. So let's just start with this top left one, those 19-year-olds who lived with their parents. There were 324 of them. Now what this is saying is that there's really no relationship between the living arrangement and your age. We would expect however many 19-year-olds to live with their parents from this sample of 2,984. So as I said, this expected count is found by doing the row total times column total divided by the table total, or I like to call it overall total, okay, OT. So for this row, its row total is 1357 times the column total is 540 divided by the overall total of 2,984. All right, let's do this. 1357 times 540 divided by 2984. we'll say. If there's really no relationship between living arrangement and age, across this sample of almost 3,000 people, we would have expected about 245, 246 19-year-olds to live with their parents. Instead, we had 324. There's a difference there. Is that a big difference? Is that a significant difference? That might be something that we follow up on if our test does come back as significant. Okay? But that was one of 20 comparisons that we have on this two-way table. There are 19 more to do. Okay, if we go over to this next position, this next cell, same row total but a different column total, okay, we're going to get 20 different values for our expectations across everything. It is time consuming. It is not something that I want you to do. So once again, embrace the technology that we'll be talking about in just a minute. Any questions up to this point? They're doing that here, more so with the expected values. I will say that a lot of times you'll see this presented to you, like you might see this on a homework problem or something, where they have the observed values right there, and then right next to it in parentheses, they'll have the expected value, 245.7 or whatever that was. Okay? And so each number will have a spot next to it with parentheses that have the expected counts in there as well. Okay? For easy side-by-side comparison. Now, once you have all of these expected counts, what the chi-square statistic is a summation of all of these. We're testing to see whether the observed differences among the conditional distributions are statistically significant. We compare the observed and the expected counts. Again, this is no different than what we did with the z-test or the t-test. We expected this, we got this. Okay? We have all of these differences. Instead of just a single difference between our sample data and our expectation, we now have, in this case, 20 different differences. So, the chi-square calculation looks like this. You take your observed value from your table, subtract away the expected count in each slot. You have that difference. Sometimes it's going to be a positive difference if observed is bigger than expected. Sometimes it's going to be a negative difference. Squaring them makes all of those differences positive. You're dividing by the expected count. So you have this value in our first top left cell. Then you're going to be doing this for the next cell over, and then the next cell over, and then the next cell over. This sigma means that you add all of those chi-square values together. And that sum is the chi-square test statistic. The sum is over all of the cells in the table. So in this example problem, we would be adding 20 of these together. Again, the calculator, GeoGebra will do that for you. Now, we do have some guidelines in terms of when we can use this. They're not that strict though. It says the chi-square test, like the Z procedures for comparing two proportions, is an approximate method that becomes more accurate as the counts in the cells of the table get larger. The bigger the sample size, the better. That hasn't changed. Fortunately, the chi-square approximation is quite accurate for modest counts. Okay? You're probably not going to come across a case where you cannot use chi-square because you haven't met like some minimum threshold. The rule here is that you can safely use chi-square with critical values from the chi-square distribution when no more than 20% of the expected counts are less than 5, and all individual expected counts are 1 or greater. Okay. So, in this case, you would like to look at all of the expected counts, which we don't quite have yet, so I'll show you that in a minute with the technology. But as long as the individual counts are greater than 1, okay, you might run into some problems like for an other category, like do you believe this, or are you other? Sometimes those others are like pretty small and could give you some problems. But as long as they're bigger than 1, that's good. And as long as no more than 20% of all of those expected counts are less than 5, then you're good for these procedures. These use the expected cell counts, not the observed. Okay, so you have to go through and look at those expected values. Okay, so with the graphing calculator, I am going to walk you through this, but this is what I have as kind of like a flow chart if you need to refer back to this. To show this table on the calculator, we're going to use matrices, which are always tweaking the curriculum a little bit. If you took Honors Algebra 2, you might have done a little bit with matrices. Can anybody speak to that? Yes or no? If you took academic, you definitely did not do it. But I think they might have gotten rid of matrices altogether. All we're doing with matrices are using them to represent our table. So we're going to go to a matrix, which I'll show you in just a second, input the 5x4 matrix, enter all of our values. And then we're going to perform this chi-square so that it will provide us with the expected values, and from there we can kind of go through and determine if we're allowed to do this and what are our differences. Okay. So give me a second, let me switch screens here to the calculator. Okay, so on the calculator, to bring up the matrices, you're going to press second, and the matrix button is right here. It's that reciprocal button just below map. Make that selection, and bring up this menu. The first column in this menu is just identifying the matrix. So you cannot edit it from this menu. So go over, okay, don't worry about math. I don't think we're going to do anything from here. But in this edit column, we're going to make that selection. And here is where you would enter your observed values. Okay, so you provide the dimensions, row and then column in that order. So this is a 5x4. And then you have to type in all those values. Okay? Now, it's not easy for me to do this here because it does not show all 4 columns at once. If you want to follow along and type this in right now, you're welcome to do that. The table is in the book here, page 578. If somebody wants to do that, follow along, you can grab a book, you're welcome to do that right now. But otherwise, I'm just going to kind of move forward here. So, once we get all of our observed values entered, we're going to second and quit out of this and go to the stat button and over to tests. And we are going to go most of the way down. So to shortcut that, I press up. And if you have a much older calculator, you might not have this GOF, this chi-square goodness of fit test. we'll deal with that if we need to. You'll have to use GeoGebra in that case. But for right now, we're going to do letter C, which is chi-square test. At least it's letter C on my calculator right here. Up. Letter C. Now, it wants you to confirm that your observed values are in matrix A, and it is going to create the expected values and place them automatically into matrix B. Now, if you had your observed values somewhere else, this is where you would do second matrix, and in that first column of naming it, tell it which matrix to reference. And if you wanted to put the expected values in some other matrix, that you'd also change that there. But we're going to leave this as it is. Go down to calculate. So this is jumping right to the end here. Our chi-square statistic, 193.55, we round it. P-value, 6.98 times 10 to the negative 35th power. That is an extremely small p-value. That is essentially 0. Okay, we saw that on our test. We're going to see that with GeoGebra as well. GeoGebra isn't going to give us scientific notation. It's just going to say 0 for the p-value, okay, which means at whatever alpha level of significance, this is significant. Degrees of freedom. We haven't talked about that just yet. Calculator provides it for you. I do have the equation for degrees of freedom on an upcoming slide, but it's pretty easy. You know that for degrees of freedom up to this point, we've done like n minus 1. Well, that's when we had a single variable. We have 2 variables now, so we're doing n minus 1 for both of these. So we had a 5 by 4 table. 5 minus 1 is 4. For the other variable, 4 minus 1 is 3. Multiply those two together. 4 times 3, there's your 12 degrees of freedom. Or the calculator will do it. So in this case, kind of getting ahead of ourselves because we haven't even analyzed the expected values yet, but we are rejecting the null and accepting the alternative hypothesis. We do have significant, strong, convincing evidence that there is a relationship between living arrangement and age. Any questions up to this point? All right, almost there. Let's go back to the matrices, because now let's look at those observed values or those expected values that it put into matrix B for us. Okay. I'm just having it name it and then hit enter so it brings it up on the main screen. Okay. Yeah, we have a lot of decimals here. It probably could have rounded it for us, but we'll just kind of go with it. We could look at all of these. What is kind of important for us to look at is to make sure that we meet those chi-square qualifications, which said we could not have any expected values less than 1, nor could we have more than 20% of them less than 5. So the less than 5, that might happen in this bottom row, which was the other category. So I'm just going to quickly scroll across and make sure that we don't have anything, or that we don't have anything that's less than 1, and we'll keep track of how many of them are less than 5. So we've got the 3.4, we've got, we've got 3, we've got 4.8. Actually, a better screen to do this is probably the edit screen, because it will round them. Look at matrix B. Yeah, much better. Okay, so now that bottom row, yeah, 3.4, 4.8, that's bigger than 5. That's bigger than 5. So we're good. We only have 2 values that are less than 5. 2 out of 20. That's only 10%. So we are good for our chi-square procedures here. Any questions with the calculator? let's take a look at GeoGebra. So I didn't type So this is under probability and distributions, statistics. Here's our drop-down menu for our other tests that we've done. We've got chi-square at the very bottom. There's that GOF, goodness of fit test, that we'll talk about on Monday. We just want chi-square test. So you provide it with the dimensions, 5 by 4, and we have these check boxes here. I'll talk about those in a minute. But we just type in all of our values like we had before. One of the nice things about GeoGebra is that it does allow you to provide headings here that don't factor into the calculations. So if you wanted to put like 19, 20, 21, 22, and live with their parents, live with somebody else, that sort of thing, okay, that could be organized there. Once we put in the numbers, it will perform the analysis for us. You can already see, just based off of the dimensions, it knows that there are going to be 12 degrees of freedom. Let me go back to my slideshow. Okay, so there's the graphing calculator. Again, just kind of walk through to show you if you needed to re-reference this. For GeoGebra, and all of these values put in there. You can see the chi-square value that we had from the calculator, 193.5. P-value is essentially 0. Rejecting the null, accepting the alternative. There is a relationship between living arrangement and age. Over here, I decided to check all of those boxes because this is where it starts to get a little bit messy, as you can see. Our result came back that there is a relationship. Okay, so that's good. But we can't just end there. You need to now start to analyze a little bit more. What is that relationship? And this is where these numbers can help you. And admittedly, these could be better labeled or better structured, but it is what it is. You can check or uncheck some of these. Like if you just wanted to concentrate on expected count, okay, only check that. And then when you're done with it, uncheck it, check something else. And these aren't even presented in order, okay? The first two numbers that you see under the data entry are expected count and chi-square contribution. So for those 19-year-olds that were living at home, we had an expected value of 245.57. That's right there. We have all of the expected counts right below each one of those data entries. The chi-square contribution is next. Remember that the sum of all of those values gives you that overall chi-square statistic, 193.5. The bigger this chi-square is, the smaller the p-value. Okay, it's like a one-sided thing, or I shouldn't say that. It's one direction in terms of that. If you keep adding into this chi-square count, that p-value is going to get smaller and smaller. I'll show you why that's true in a second. But looking here, like we have 25 of that 193 just from that first spot. Compare that with something else over here, like what do I want to see? This spot. These were 21-year-olds that lived with somebody else other than their parents. Okay? only 0.279 of that 193 was contributed by that. Because there was a small difference between what we observed with 40 and what we expected with 43.48. This sort of an analysis is now what is important to you in terms of determining where do those differences occur. Okay? It looked like the 19-year-olds who live with their parents, that's an important difference. Okay? The 21-year-olds who live with somebody else, that's not an important difference. We continue to go through all of these. The last ones, the row percentage and the column percentage. These were the conditional calculations that we talked about at the beginning of the lesson. GeoGebra will do this for us too. Okay? It's kind of hard to see here. We had said that the column percentages were relevant. The row percentages in this case, not so much. So those 19-year-olds who live with their parents, that is the column percentage. It's the last number under this data entry. 19-year-olds there, that was 60%, like we said. So if you needed to have those values quickly calculated for you, GeoGebra can do that. You do kind of have to sort through it and see what's relevant. Any questions so far? We're almost done. Trust me. When you're using the technology, again, chi-square is an overall test for detecting relationships between two categorical variables. If the test is significant, now your work begins. Okay, you have to look at the data to learn the nature of the relationship. We can compare selected percents. Okay, maybe you're going to do a z-test, a difference of two proportions test now between like 19-year-olds who live with their parents and 20-year-olds who live with their parents, something like that. Maybe now that you've isolated relevant relationships, now you can start to have some direction as to what z-test would be appropriate. Or you could compare observed and expected cell counts, kind of like we did here. Okay, the 21-year-olds who lived with somebody else, that wasn't really important for us. Okay? It tells us which cells have more or fewer observations than we would expect if that null hypothesis is true and there's really no relationship. We're also looking at the terms of the chi-square test statistic. Which cells contribute the most to the value of chi-square? Like we saw, 25 of the 193 or something were from 19-year-olds who live with their parents. This is where we're going to end here. The test that we've looked at up to this point is called a chi-square test of independence. All of these examples have been questions about whether the two classification variables are independent or not. That contributed to our expected counts. Okay, we followed that basic equation for independence. Another variation of this test that we're going to see on Monday is a chi-square test for homogeneity, which is essentially testing to see if our values came from whether or not the populations from which the samples were selected, are they homogeneous? Are they the same? Okay, with respect to this single classification variable. The procedures themselves are identical, okay, in terms of like entry into the calculator or GeoGebra. Okay. There's just a slight twist in the interpretation of what you're doing for the test of homogeneity. Okay. The other thing we're going to look at on Monday is the goodness of fit test, okay, that we saw as one of our other options. Okay? So we'll do that. Last thing, jumping ahead here, but this is what the chi-square distribution itself looks like. It directly depends on the degrees of freedom that you have. Unlike the z and the t, we are no longer a bell curve. We are no longer a uniform mirrored distribution. Instead, we are heavily skewed to the right. We have just 1 degree of freedom, meaning we have a 2 by 2 table. We see that heavy skew right there that basically looks like an inverse function. We have a peak when we have some of these lower degrees of freedom. In our example, we had 12 degrees of freedom, so we're going to have our peak kind of flattened out here, and it's going to extend out to the right. So that chi-square statistic is along the x-axis. So we had our 193 or something like that. That's way out here on this skewed right distribution. The p-value represents the amount of data in the tail and to the right. Okay, always. So the p-value in our problem that was like something times 10 to the negative 35th power, essentially 0, that tells you about the skew, how far off to the right this is, and how unlikely it would be to get that p-value. I'm done. Any questions? I know there's a lot here, okay? We spent an hour with 1 example problem going through the procedures, and we still have 2 more chi-square tests to look at. We'll do that. We will look at plenty more examples, and we're going to look at some simplified examples too. Some of these 2 by 2 tables to really see kind of some of the intricacies of what's going on in that case. All right? So we'll take a look at this Monday and into next week. Right? And we'll get a homework assignment next week. We'll go from there. Okay? I'm working on grading those things. Hopefully I'll get some of those updated in the grade book over the next couple of days. All right? Have a good one. Those of you at home, free to sign off. I'll see you.